Okay, thank you everyone. First, thank the organizers for the invitation. Very happy to be here. I'm coming from Dartmouth College. I'm also an Amazon visiting academic, so I'm also here talking on behalf of my academic side, but I will mention some things about Amazon Broadcat at the end. Today I was tasked with giving the overview of quantum chemistry, and I think quantum chemistry is a very fascinating field. I'll give a nice overview of what quantum chemistry is, but what I'd like to maybe start off with is maybe just to introduce the idea of what is computational chemistry. So chemistry, when I first went to my first internship, when I was a junior, I went off to Berkeley to work with a computational chemist, and I asked the graduate student I was working with, why do we do computational chemistry? And he said the goal is to put the wet chemists out of business. And if not put them out of business, at least support their work, help them understand their experiments, understand why this occurred, why this did not occur, and help them identify what the next experiment should be. So I'll mention machine learning. Thank you to Alex for giving us a nice introduction there. But first, let me start off with a little bit about what chemistry is. So chemistry is often called the central science, and it connects biology and life sciences to physics and mathematics on the other side. So chemistry is right there at that interface. We can zoom in from what chemistry is, thinking about molecules, transformation of matter, states of matter, and how these transformations occur, to physical chemistry, where we're taking chemistry informed by physics. There's a lot of physics in the world. We're here talking about quantum convening. However, physics is not limited to quantum mechanics. And so one of the things I will emphasize here throughout this talk is how much classical mechanics plays a role inside of quantum chemistry. So the first line here I have here is computational chemistry. So computational chemistry is using computers to do chemistry. You could do physical chemistry where you use physics, say lasers, to understand a molecule or a reaction. And so you're using physics to still interpret the experiment. However, if you're going to use computers to do so, you can use something like molecular dynamics, which is classical physics. It's classical physics informed by quantum mechanics, but you're doing classical equations of motion, force fields, moving everything along. We go beyond molecular dynamics to think about quantum chemistry. We're talking about quantum mechanics, quantum mechanical objects, and that really comes down to electrons dictating the behavior of the atoms that they're around. This leads to a lot of ideas of strong and weak correlation and molecular orbitals, which I just have here as side notes. If you have questions about those things, hopefully they'll be addressed at some point during this talk. If not, questions later. Okay. So here, I want to give the main idea of what computational chemistry is with some examples, some illustrations, and maybe try and walk you through this as best I can. Do I have a laser pointer? How does this work? Yeah, I'm just trying to decide, do I point here or there? I see. I'll use the mouse. Do I have a mouse? I'll use a laser pointer. You guys, good luck on this side. Everybody over there. Okay, so, laser pointer. Okay, so the thing I want to point out here first is that when we think about computational chemistry, when we think about chemistry as a chemist and think about computational chemistry as something that chemists use. Chemists are interested in molecules, here in blue, in the blue box, and they're interested in physical quantities. The computation in the middle is irrelevant to a chemist who is in a lab mixing chemicals. They want to know the answer, and they want to know nothing about why the answer worked. The analogy I like to give a lot of times when thinking about this is the mechanic who's designing a race car for a driver. If you're a mechanic who designs a race car for the driver, well, the driver doesn't need to know everything about that engine. He doesn't need the specifications, the cam cycle, all these sort of things. Just, hey, do I step? Does it have good pickup on the front end or the back end? And so from the same idea, chemists are quite interested in these physical quantities, but the computation is somewhat irrelevant from their point of view of getting out physical quantities. From a computational point of view, there's a number of things that we have to do. We have input states and input Hamiltonians, but we need to discretize these things. We have the descriptions of them as Coulombic interactions, 1 over r, or as some kinetic energy operator. But all these things have to be discretized in some sort of basis. And then once we have that, then we have to perform some computational task, either time propagation here, or finding a ground state or different eigenstates of the Hamiltonian. And the output of this would be some energy function as a function of the coordinates, or some time-dependent wave function as a function of time. In either one of these cases, two very separate problems, and we'll come back to this point in a minute, but these are two separate problems that are both of interest for quantum chemists. So let me talk about the first one, about computing the energy, and that's what this plot is over here. So when we think about computational chemistry, in many ways, there's a lot of physics and a lot of chemistry here. However, the goal of solving the eigenvalue problem is to get out the red eigenstates. So this curve here is one of the eigenstates, it's another eigenstate, and this is eigenstate number 0. So 3 different eigenstates of your Hamiltonian, and what happens is as we change this reaction coordinate, this is some r, the eigenvalues change. The eigenvalues of the Hamiltonian change depending on where the nuclear configuration is. This is called the Born-Oppenheimer approximation, and the way I like to visualize this, at least verbally, is if you imagine someone who has a walker walking through a room full of kids, and all the kids are bouncing around, running, whatever. Well, as this person moves, all the kids are going to rearrange themselves according to where that person is. So there's 2 or 3 old people walking around, well, the kids are going to try not to bump into them, but from their point of view, these old people are standing still. And the kids are running around so fast that it's no difference. And so for molecules and atoms, there's a huge mass separation, 3 orders of magnitude, 4 orders of magnitude, between the electron and the protons or atoms that you're, or the atomic systems you're looking at. So that means that you can treat the electrons as if they're buzzing around, solve the electronic problem with the nuclear motion fixed, called camp nuclei, lots of things there. And so what you're seeing here is a plot of the static energies of the electronic system. Why we only have ground states for electronic systems, so I have here these little H bar omegas. And so each one of them, I tried to color code it a little bit. So here's yellow, one of our lower frequencies. This is a very small energy level gap between the vibrational modes of your system. And so what you want to think is that there's some molecular system that's breathing in and out at the bottom of this well. And it breathes in and out depending on what state it's in, but that's a very low energy excitation. And so that is at the thermal room temperature that we're at. So most things are vibrating at room temperature. They're moving around a bit inside the ground state electronic potential. However, the separation between the ground state and the excited state is large enough that this is nothing comparable to room temperature. So it actually ends up being that you almost are always inside your ground state unless there's a photon with the appropriate amount of energy to take you from the ground state to the excited state. There should be some electronic transition here. Or if you had a really strong laser and you have enough energy inside that photon to take you to an ionized state and you lost an electron. This photoelectric effect that Einstein laid out. From these potential energy curves, you also have things like your reaction energy, your transition states, what the geometries look like, what happens if you get excited to this state and you decay, some different pathways. So all these different pathways are relevant for what happens to the molecular system when a chemist is actually doing an experiment. They do not care about this picture, they care about the reaction pathway and what the energy of the photon is to dissociate this molecule or to ionize it. And so again, the point is the physical quantity that they want. Some other examples are just proton affinity, barrier height, so you're rotating this molecule through a plane and seeing what the energy differences are to figure out what the configuration might be at room temperature. The reason that we think about room temperature is because most chemistry happens on Earth, or at least the ones that we're interested in, at 300 degrees Kelvin or so. And so this is where a lot of the motivation is coming from and looking at quantum chemistry at the accuracy level that they do. Okay. All right. Lin Lin is a professor of mathematics at Berkeley, and he wrote a mathematical introduction to electronic structure theory. It's a nice book if you guys want to get some pretty nice introduction to electronic structure. Okay. So one of the points that I brought up last time was this idea of discretization in quantum chemistry. This idea of discretizing your system is just saying that if I had a continuous system, a water molecule, well, that water molecule I have to put into some numerical representation. How many points do I use for that numerical representation will determine how large my matrix is. So if I have a very large matrix, then if I use many different orbitals, each one of these orbitals, these basis functions, are single particle wave functions. But when we want to talk about a molecular system, we need a multi-particle wave function. So we build it up from these single point orbitals, plane waves, orthogonal polynomials. And the idea is you want to capture the correlation of these different atoms. And interestingly enough, one thing that's worth pointing out is that if the electrons don't interact at all, the problem is easy. So if the electrons do not interact at all, there's a whole formulation called match gates, free fermions, that really allows you to do the simulation without a quantum computer. If you can do it without a quantum computer, that's great. And so when you look at what happens in quantum chemistry and you have weak correlation, you're very close to being a free fermionic system, and then you can get away with classical simulation. A lot of this comes down to how the basis set is constructed, and so constructing basis sets that make your problem harder or easier. You can imagine that if you only have a few points, then maybe it's a very easy problem to solve in practice, and then as you try to go to higher accuracy by adding in more basis functions, then you end up with a harder problem. So this is really thinking about the complete basis set limit. How do we get back to the continuum limit? Do we even need to get back to the continuum limit if we're only interested in temperatures at the thermal energy of the room? Okay. All right. So there's an active area of research, machine learning. We heard a nice talk about this. Here's a diagram that I took from my former advisors in silico experiments. There's a large amount of ideas here. So again, calculating electronic energies and other properties is what the goal is. So remember, the outcome goal is here. And machine learning kind of just pervades everything in the middle. And I think I'm going to skip the machine learning discussion, not entirely, but to point out that machine learning is predicated on having good data. So I think we can all at least take that as a nice, easy point to start. And if we think about machine learning needing good data, we can think about how does machine learning get these data sets from quantum chemistry. And it would be by using the de facto standard for training data, which is density functional theory, which is highlighted here. It's one of these methods inside this chart. The other methods that are listed at the top are more advanced methods that have higher computational costs. All right, so DFT, it would be remiss of me to give a talk to a bunch of mathematicians that is introducing the overview of quantum chemistry without talking about DFT. All right, so here, this is just a probability density. So the idea is that if I have a probability density rather than the full wave function, if I have the full wave function of all electrons, so all n electrons, then I need 3 n coordinates. If I just have a probability distribution, then I just have one electron probability distribution, so it's just a, oh, there it is, upgraded, nice. Yeah. 3 n coordinates, and just 3 coordinates for probability distribution. So probability density replaces the wave function, and this is the entire basis for density functional theory. You make functionals of the density as a probability function, and then get back energies as functionals of this. It's a very interesting mathematical story. Maybe to give a very brief overview of it, is that the ground state and the external potential, whatever the nuclear configuration is in one-to-one correspondence with the probability density of the ground state. If you go from one problem to the next problem, the only thing that changes when you talk about the Hamiltonian is where the nuclei were, or whether you applied an electric field or not. The kinetic energy term, which is this T here, and the interaction term, the Coulombic interaction, don't matter from one system to the next, right? You just move around the nuclei, and then everything else about the Hamiltonian stays the same. So there's something called the universal part of the Hamiltonian. This is this universal part, this is kinetic energy and the interaction term. And then the remainder is just this external potential. And you just predicate the density and the external potential. And maybe if you think about it, oh, actually it's here, right? So this is really nice. This equation here kind of is the crux of why this works. So the density, this n of x, this density at all points is the only part of the wave function that couples into the external potential. And so you get this nice one-to-one correspondence of being able to work with just the density. It's theoretically impossible to get perfect density functional theory for this functional for a lot of computational reasons. But what people do in practice is approximate. They've been doing this for almost 100 years. So there's a lot of really, really good approximations for ground state density functional theory. All right, so maybe to put in a few key considerations. I mean, it's about math, right? So, but I don't have that many equations, but maybe to give you some points here to think about where the math comes in, is that there's this idea of how you're approximating the problem. So this Hartree-Fock density functional theory, again, this is the exact diagonalization of the problem. Start adding in more physical corrections. You can keep making it more and more in advance until you start adding in, I don't know, high energy physics corrections, all sorts of things can go into this, and just increases your approximation level. Increase the cost that you have to do in order to understand your system at different amounts of resolution. The resolution is how are you describing the system. So you just describe the valence electrons, maybe the valence in the core electrons, maybe multiple orbitals for the valence, and then you go to infinite flexibility where you're in some continuum limit. That would be physical reality over here. So as we go up on this plot, you have more and more descriptive resolution, and you're treating it more and more accurately. So there's two axes you should think about improving quantum chemistry. One is how we're treating the system, one is how we're discretizing the system, and that's these 2 points here. This point about accuracy of physical relevance. So if you were doing spectroscopy of atoms inside of outer space, then you might need a much higher precision than you would need for thermal energies on Earth. So depending on your application, you may need different approximations. And so this is really part of the dependence on who's asking the question. And as the computational designer of the algorithm, it doesn't matter who's asking the question. It matters that you are able to give out good answers. Okay, resources, energy, and time. So this is thinking a lot about quantum computing, a lot about exascale computing. How much energy does it take to run this computation? Matters. How long does it take? Boom. Yeah, as was mentioned in the introduction, there's a practical introduction to quantum computing. And so I won't say too much about this. There's 3 areas we heard about yesterday from Jake Taylor. Quantum simulation, there's a number of experimental realizations, they're mostly minimal basis sets. Because they're in minimal basis sets, the actual usefulness that these experiments have is extremely limited. You don't have large enough basis sets to capture the descriptive resolution to talk about the system, even if you're doing a very high approximation level. Quantum programming, Amazon Brocket, QuizKit, lots of different packages are available. The NISC error centers around optimization. I'm going to say a bit about how I don't think optimization is the right direction in a moment. But yeah, okay. And a lot of my work, just to kind of plug my own research group, is taking this fermionic algebra and putting on the spin algebras and thinking about how do we actually do the simulation on a quantum device. Okay, so this is a really nice picture. I remember when I was a graduate student, I had to do rotation inside of one of the labs, and Eric Heller had us just read this paper for the entire time. And it's a very nice paper from Zurich. If you've not read the paper, it's really nice discussion of decoherence. And so what I wanted to point out here is that there's a quantum domain over here and this classical domain. And so what I'd like to have you think about is rather than quantum domain and classical domain, and in particular one of the things I'd like to point out is that in this classical domain, if you look, this is classical order, Newton's equation, second law of thermodynamics, fluid, and planets and suns. But what I think you should be thinking about instead of classical mechanics is stochastic situations. So if you have probability distributions, then you are much closer to what we talk about in quantum mechanics. I'll talk a little bit more about this in my last 7-8 minutes. And so the dividing line between them is statistics. The dividing line between quantum and classical algorithms is statistics. And so really thinking about how do we draw the statistical line between the two is fantastic work for anybody who knows probability or statistics. And that, I assume, is a lot of the applied mathematicians in the room. I was having some discussions last night at dinner, and I realized that there was no discussion of quantum primacy results at all so far, and so I wanted to point out a few. So Google in 2019 put out a paper saying about quantum primacy, and this is a little digression from quantum chemistry, but no issue here, hopefully. So you have some input, you do some quantum algorithm, you get some output, and you want to know, if I did this, can I get out some result that I couldn't do any other way than using a quantum computer? That is the definition of quantum primacy. There's a whole bunch of asterisks about whether it should be quantum primacy or supremacy. This is a political discussion I don't want to enter into. I prefer primacy just to avoid it, but yeah, feel free to look it up. Okay, underlying again the statistical arguments. There was, so I updated the slide just today, so I just pulled the most recent papers I could find. This is from Quantinium. This is from earlier this year, from the middle of the year, where they just did the same experiment Google did, but bigger. So people were continuing to do these quantum supremacy experiments and building up the data set and trying to make arguments. Now, we're in a room full of mathematically minded folks, so let me point out some of the main mathematical arguments against quantum supremacy and point out that they are mostly, well, the first type of attacks on quantum primacy are statistical attacks. Statistical proofing. So it's saying that I'm not even going to try and do your quantum computation. I'm just going to cheat the benchmark that you made. I'm going to get another algorithm that's going to take the circuit that you have and somehow cheat it. I'm going to split it up. So I don't know, this particular paper actually found just 2 random articles in the archive. In most of these ideas for classically spoofing systems, the idea is that we're going to take this benchmark and recognize when we can split it up into separate components. We split up into separate components and we stitch them back together. As long as we can do this in a way that works, we can cheat the benchmark. And so this is one of the ways that people are doing a lot of statistical gaming here and thinking about what statistics can we measure efficiently to actually determine the difference between quantum and classical. So as we pointed out many times yesterday, if you have a probability distribution, you can't pull out the whole probability distribution. You can pull out samples from it. So how do you sample and tell the difference between the two? And that is really a question between statistics and quantum mechanics. Finally, there's also, we've heard a lot about tensor networks. So this is just tensor networks. You can just simulate the system and do the best that you can. Okay, so fundamentally, the question at the heart of quantum computing is what is the difference between quantum and probability theory? This is my way of thinking about it. Whenever I talk to my graduate students, it's always probability first. What are you talking about? Is this interesting as a probability question? If it's not an interesting probability question, we probably shouldn't be doing it as a quantum question. Okay, running out of time here. All right, so a few more things I want to really underline here, since this is my chance to kind of get in the soapbox and say things that I think are important. One of the important things that I think, if you're new to this field, to recognize is that there's a huge difference between dynamics, doing time propagation, and finding a ground state or optimizing the problem. If you're optimizing a problem, it's still an optimization problem. Quantum optimization is still optimization. Optimization's hard, formally speaking, unless you have some really nice work like from our colleagues at Argonne. But if you don't, it's just an optimization problem. It's NP hard in the good case, and it's QMA hard, which is even harder. And so there's no real, in my opinion, there's no easy wins here. There's no theoretical promises there will be a win, nothing that you can really hang your hat on. You might win just for heuristics reasons. But on the other side, if you do dynamics, quantum dynamics is quantum computation. This is how you should think about what a quantum computer does, is that it does time propagation for a quantum system, and you can control what the time propagation is. Okay. I'm almost at the end. I just had a few last things to plug. This is perfect, actually. I got 3 minutes left. This is perfect, right on time. Good, good, good. Okay, here, this is my research group. So we have fantastic people. So Brent just got back from Phasecraft. Exciting times. This is my group at Dartmouth. Also, I am an Amazon visiting academic. One of the things that I did while I was there was help create this learning plan. So if you guys are interested in Amazon Braquette, thinking about how do you actually run problems on quantum computers, scan the QR code, learn a little bit about what's available for quantum computing. We also have a quiz kit demonstration later during the conference. And so if you're interested in using quiz kit with Amazon Braquette, you can, of course, use QuizKit as a provider for Braquette. I would like to highlight, again, these 5 key takeaways. Density functional theory is our baseline comparison. If we're going to build a quantum algorithm and say that it's better than DFT, then we've done something that's of interest to Bayer Pharmaceutical, to chemistry departments across the world. However, it's a long road before we can say something that's of interest that is better than density functional theory. I will say that time-dependent density functional theory has a lot more room for improvement. And so if you think about problems that you should be attacking with quantum mechanics, thinking about time-dependent problems is, I think, the right way to really get some theoretical grounding and foundation for what you're doing. All right, chemistry connects to central science. If we have a better quantum computer, the thing that I think we would use it for is getting better quantum data to do better machine learning problems. So I don't think it's separate. Getting the ground states, not doing the propagation. And the last thing that I have here, since I still have 2 minutes left, is just a little bit here about some outlook. So on one side, we have quantum advances. So quantum hardware advances, it's advancing. Will it get us anything? Who knows? But we're definitely going to build this device. There's too much money on the table for it not to get done. How good it gets in the end, we'll see. Quantum error correction is one of the main things that's going on inside of industrial pursuits. So thinking about how do we actually correct and prepare and hold information. In our last talk, we heard about some of the issues around big data for quantum computers is really around having memory to hold that data. So we can't do database search if we don't have quantum data, and to have quantum data, we need to upload it to a quantum database. And that is just the quantum memory. So this is one of our first problems. One of the things that my group works on is doing quantum simulation as quantum error correction. So when you do quantum error correction, a lot of the discussion comes around these excitations called Majorana excitations. But Majorana excitations are basically electrons in some very, very high level view. On the other side, in classical advances, put that up in a second. Exascale computing is, fantastic and new. Everybody's excited about this. What can you do with this? It's really exciting. But it's also very costly in terms of energy and in terms of other ideas there. Machine learning, very interesting. Solvable chemical instances is one of the areas that I think really has a lot of room for improvement in technical advances, thinking about how do we actually make arguments for what problems we can solve with current computers and what problems we cannot. Okay, and then just to kind of leave this here, I'll leave these questions up just because the next thing up in the next 4 seconds is to have a discussion. So here's my preloaded discussion prompts.